In 2016, a spacecraft dropped into orbit around Jupiter and started finding things that should not be there. At the center of the planet, instead of a solid rock core, it found something half melted, blending into the gas around it. A storm wider than Earth has been shrinking there for over 100 years. Lightning flashes in clouds too high and too cold for lightning to exist. Storms line up at the poles in perfect geometric shapes that refuse to merge. Jupiter is the most studied planet in the solar system, and it still doesn't add up. Here are 6 mysteries about Jupiter that scientists genuinely cannot solve. Swarms that don't manage. Jupiter shares its orbit with 2 enormous swarms of asteroids called Trojans, more than 10,000 of them, one running ahead of the planet and one trailing behind it, both locked in place by Jupiter's gravity at points called Lagrange points. On paper, the 2 swarms should hold roughly the same number of asteroids, since both sit in equally stable pockets of space along the same orbit. They don't. The leading swarm has about 60% more asteroids than the trailing one, a gap astronomers have measured and remeasured for decades without a clean explanation. In 2023, a team led by Jian Li at Nanjing University proposed that Jupiter itself is the reason. Early in the solar system's history, the planet may have jumped rapidly outward from the sun over a short window of time, a sudden shift that would have destabilized the trailing swarm far more than the leading one, freezing the imbalance in place for billions of years. The math from the research lines up with the observed 1.6 to 1 ratio almost exactly, which is why it's now the leading explanation. But it depends entirely on a migration nobody was around to observe, reconstructed from asteroid counts billions of years after the fact using simulations, not direct evidence. NASA's Lucy spacecraft, launched in 2021, is now on its way to fly past several Trojans in both swarms starting later this decade, and scientists are hoping the close-up composition data will either back the jumping Jupiter model or force them to start over. It's the best explanation anyone has offered. Nobody has proven it's the right one yet. But an uneven asteroid count is nothing compared to what's happening inside the planet itself. Core that is not solid. For decades, scientists assumed Jupiter had a small, dense core of rock and metal buried under thousands of miles of gas, the same basic blueprint every planet is supposed to follow, layered neatly from a heavy center outward. Then NASA's Juno spacecraft spent years measuring Jupiter's gravity field closely enough to map the inside of the planet directly, orbit after orbit, and what it found broke the model completely. Jupiter's core isn't a tight ball at all. It's enormous, stretching across a huge fraction of the planet's interior, and it doesn't have a clean edge. It blends gradually into the surrounding hydrogen instead of stopping at a boundary, which is why scientists now call it a dilute core, a smear of heavy elements and gas rather than a defined lump sitting at the center. One leading explanation is that a massive collision early in Jupiter's history, possibly with another young planet still forming nearby, stirred the core before it ever had the chance to settle into layers, leaving it partially dissolved for 4.5 billion years. If that's true, Jupiter's formation was far more violent than any research ever accounted for. Deeper still, the pressure gets so extreme that hydrogen itself stops behaving like a gas and turns into a strange metallic fluid capable of conducting electricity. The layer scientists believe generates Jupiter's magnetic field in the first place. But Juno's data still can't say exactly how large the dilute region is, how far it extends toward the surface, or whether it's still slowly settling today, one gravity measurement at a time. A blended, unsettled interior is strange enough on its own. What Jupiter is doing on the outside is stranger. Storm. That is shrinking. Jupiter's Great Red Spot is a storm bigger than Earth that has been raging continuously for at least 2 centuries, and it's getting smaller. 100 years ago, it was wide enough to fit 3 Earths across. Today, it's barely wide enough for one, and telescopes, including amateur ones, keep clocking it shrinking further almost every year. Storms this size aren't supposed to hold together for centuries in the first place, let alone lose that much mass while staying just as violent the entire time. A 2024 study built a 3-dimensional simulation of the storm and found it may be surviving on a kind of diet, absorbing smaller storms that collide into it from the surrounding atmosphere and feeding off their energy the way a fire needs fuel to keep burning. When fewer small storms happen to drift into it, the red spot weakens and shrinks a little more, storm by storm, year by year. Juno's instruments have measured the storm reaching roughly 200 miles deep, far deeper than anything on Earth, meaning its roots run well past the visible clouds and into the planet itself, with winds inside it clocked well above 400 kilometers an hour. Voyager photographed it in 1979 as a sprawling giant. Juno's more recent flybys show a noticeably tighter, more compact storm, the same shrinking trend caught decades apart. Scientists still don't fully agree on what sets its color, why it formed exactly where it did, or whether it will keep shrinking until it disappears completely, stabilize at some smaller size, or break apart into pieces nobody can predict yet. If a storm feeding on other storms sounds strange, Jupiter's lightning is even more weird. Lightning, where it should not exist. On Earth, lightning needs deep, cold clouds packed with water and ice, colliding over and over to build up enough electrical charge low in the atmosphere before it discharges. In 2020, Juno detected lightning striking in clouds far higher up in Jupiter's atmosphere than that process should ever allow, in a layer too cold and too thin for a normal thunderstorm to form at all by Earth's rules. The explanation scientists landed on involves ammonia. Jupiter's upper clouds contain ammonia gas that mixes with water, and that mixture lowers the freezing point enough to keep droplets liquid at altitudes where pure water would already be frozen, solid, and inert. Those liquid ammonia water droplets can still collide and separate charge the way ordinary raindrops do on Earth, just happening much higher up in the atmosphere than anyone thought was physically possible before Juno's data came back. It's a mechanism built from chemistry that doesn't exist anywhere in Earth's atmosphere, and it means Jupiter is generating storms in a part of the sky scientists had written off entirely as too cold to matter. On Jupiter's night side, this shallow lightning flickers almost continuously in certain regions, closer to a standing electrical storm than the isolated bolts we see back home. But researchers still aren't certain exactly how much ammonia is required to trigger it, or why this shallow lightning shows up in some storm systems and stays completely absent from others on a planet covered in nearly identical clouds. Jupiter's storms don't just strike in strange places. At the poles, they've organized themselves into shapes that shouldn't be possible. A cyclone no one can enter. When Juno first looked straight down at Jupiter's poles instead of past them, it found something no researcher had predicted: rings of giant cyclones, each one hundreds of miles wide, circling a central storm without ever merging into one larger system. The North Pole has 8 cyclones surrounding a 9th at the center. The South Pole originally had 5 surrounding ones, forming a near-perfect pentagon until 2019, when a 6th cyclone appeared out of nowhere and reshaped the whole formation into a hexagon overnight by planetary timescales. NASA scientists described the pattern as behaving like a private club that resists new members, spinning close enough to touch without ever combining into a single, larger storm the way weather systems normally do everywhere else. On Earth, storms packed this tightly would collide and merge within days at most. On Jupiter, this exact arrangement has held stable for years at a time, each cyclone spinning with winds strong enough to flatten a city, yet somehow keeping a respectful, fixed distance from its neighbors the entire time. One theory suggests the cyclones repel each other through their own spinning winds, locking into a stable geometric formation the same way magnets settle into a fixed pattern rather than colliding into one. But nobody predicted this shape before Juno arrived, and nobody can yet explain why the number settles where it does, or what happens the next time the club gains or loses a member. Every one of these mysteries, the core, the storm, the lightning, the cyclones, traces back to something even stranger happening deep inside the planet that's still ringing. Jupiter's magnetic field isn't uniform across the planet. Its northern hemisphere is scattered with patches of unusually strong, concentrated magnetism that don't resemble anything seen on another planet in the solar system, while a single isolated feature near the equator, nicknamed the Great Blue Spot, drifts slowly eastward year after year, decade after decade. Harvard researchers studying years of Juno's magnetic data found that the Great Blue Spot doesn't just drift at a steady, predictable pace. Its motion pulses on a roughly 4-year cycle, speeding up and slowing down in a rhythm with no obvious cause visible anywhere on the surface. The likely explanation is that Jupiter's interior isn't sitting still, even now. Deep inside the layer of metallic hydrogen that generates the planet's entire magnetic field, waves may be moving through the fluid itself, the same way sound waves move through air on Earth, and those waves are surfacing as this pulsing magnetic signature scientists can actually measure from orbit, millions of miles away. In effect, Jupiter's core still seems to be moving 4.5 billion years after the planet finished forming out of the same cloud of gas and dust as everything else in this solar system. Researchers have compared the pattern to a kind of slow-motion ringing, waves sloshing back and forth through metallic hydrogen the way a struck bell keeps vibrating long after it's hit, except this bell has been ringing since before Earth had an atmosphere. But scientists don't yet know what's driving those waves, how deep inside the planet they originate, or what else might still be shifting inside a world everyone assumed had long since settled down for good. A core that never fully solidified, a storm shrinking after 2 centuries of raging, lightning striking where the chemistry shouldn't allow it. Cyclones locked in a formation that refuses to merge. A magnetic field pulsing like something underneath it is still moving. Jupiter is the planet we've studied longer and closer than almost anywhere else in the solar system, and the closer we look, the less settled it turns out to be. If one of these mysteries stuck with you, subscribe, because we're going to keep finding the places in the solar system that still don't add up.